All right, I'm back. Let's do more. We just did A, so why don't we do B now? Seems right, right? Seems like we should do B. Uh, Come on, clear annotations. All right, put B on top of A. We'll do this one. It's gonna be the same deal. It's another rational function, so you should be thinking all about how rational functions just have discontinuities at the zeros of their denominator. So this one is actually a pain in the butt, and I'm thinking I probably just made a mistake because the denominator is not factorable. You can't factor it, which is fine. There's still ways to find the zeros, right? And the way that you find the zeros is you use the quadratic formula, which is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Am I going to ask you to do this on the quiz? No, I'm not. Maybe someday in the future I'll ask you to do it because, I mean, it's important. You're supposed to know it, and it's not hard. But whatever day I ask you to know it, I will have taught it to you more explicitly first. So let's not do this one. You have an answer key on this anyway, a paper pencil answer key. So if you're desperate to know what those values are, just look on the answer key and you'll find them. Okay, hey. I feel like I have your attention right now, so I just went and got the notes from the answer key. So just so you know, I mean, if you're using the formula, you could plug in, you could do this math, and what you do is you arrive at these two answers. So those are the zeros, whatever the heck that is. I don't know what it is. But negative 3 plus root 6, that's some number, and you know there's a vertical asymptote there, so it's an infinite discontinuity. And then negative 3 minus root 6, that's some other number, and you know there's another vertical asymptote there, so they're both infinite discontinuities. And I'm explaining up here how, since the denominator can't be factored, you'd have to use the quadratic formula to find the zeros. That's it. The only thing worth mentioning here is, what if you had used the quadratic formula, and then this guy here that I have talked about a lot, he's called the discriminant. Well, if that discriminant came out to be negative, b squared minus 4ac, if that was less than 0, then you'd be trying to take the square root of a negative, and that would mean that your only zeros are non-real. That would mean that this particular rational function doesn't have any discontinuities, and it would therefore be continuous from negative infinity to infinity. And yes, I put this on the quiz. So some of you saw the x squared plus 9 in the denominator of some function, and you are expected to say that because the denominator does not have any real zeros, the rational function doesn't have any discontinuities, and therefore it's continuous from negative infinity to infinity. So could I put that on an assessment? Yeah, I already did. It was on quiz 3, at least one of the forms, form A or form B. All right, moving on. All right, H looks like it's easy peasy, so I'm going to go through it really fast. But factor x minus 2, factor x plus 1, x minus 1. This, I don't know why I even asked this, honestly, because it's basically the exact same as part A. You have two zeros. You have a 0 at x equals negative 1, and you have a 0 at x equals 1. And since neither of them cancel, they're both vertical asymptotes, which means they're both infinite discontinuities. And you would justify those the same way we justified them before. I'm done talking about C. Let's do D. Throw that in the garbage. So D. For D, we got this piecewise function, and this is a little more important. So what do we got? This piecewise happens to be made out of 3 different functions. It's made out of the pink one, the green one, and the blue one. And your thought process here, hopefully, would be that if you were analyzing this whole thing for continuity, you would say for sure, well, x is continuous everywhere. So since we're defined for all the x's less than 0, that x function is definitely telling me that we're continuous from negative infinity all the way to 0. Then the next function kicks in, and it's quadratic. It's just a parabola, so he's continuous everywhere. And since we're only using that from 0 to 2, I can rest assured that we're continuous from 0 to 2. Then the next function kicks in after 2, and it's another line. It's 2 minus x. That line would just have its y-intercept at 2. It would have a slope of -1, so it decreases. But it's just a line, and lines are continuous everywhere, so for sure I can say that from 2 to infinity, we're continuous. So who's the only thing that we should care about? Well, 0. What's happening right at 0? Are we continuous, or do we have some kind of discontinuity? And you should also care about 2. What's happening right at 2? But that's it. We have to test just those two values. So how do I test them? I check my limits and I check my function values. So at 0, I would certainly be concerned about the limit as I approach 0 from the left. And guess what? The limit from the left is coming from this red function. So the limit as x approaches 0 from the left of this function, I get that by just plugging 0 into this function, which is literally just x. So you plug 0 in for x and you get 0. Then if you want the limit from the right, that's going to come from the green function. And we're now doing the limit as x approaches 0 from the right of the function f of x. That's coming from the green function, which is x squared. And guess what 0 squared is? It's still 0. So far, it's looking like maybe we're continuous because the two limits are equal. But there is a chance that my limit from the left was giving me 0, and my limit from the right was giving me 0. But maybe, just maybe the function value is something else. Maybe the value of the function's up here, and then I get a point discontinuity. But that's not the case because, of course, the actual function value, f of 2, f of 0. Well, 0 belongs to this middle interval. See how it says we can be 0? So f of 0 would come from the same x squared that gave us our limit. So of course f of 0 is 0 squared. And I am getting 0 again, so that's no such luck. We don't actually have a point up here. The value of the function is right there. And so everything is nice and neat, and we are continuous at 0. Why'd that happen? Separate. Throw that. Oh no, something's still connected. Hold on. I can do this. I think that's good. Okay, so all this math right here proves that f of x is continuous at 0. Exclamation point. Oh, by the way, what does that mean about our intervals on which we're continuous? Well, I don't need separate red and green intervals anymore because right at 0, we are continuous. So we should probably put those two intervals back together again and say that we're continuous from -infinity all the way up to 2. Now, I'm still not convinced that I'm continuous at 2. I might not be. So we've got another round of testing the limits. So I'll shrink that down. And this time I want the limit as we approach 2. Notice 2 is at the end of the green interval. So as we approach 2 from the left, we're now using the green expression. So what is the limit as x approaches 2 from the left? Well, it would be given by the green expression, the x squared. So it'll be 2 squared, and it's 4. My left-hand limit is 4. Now my right-hand limit as I approach 2, well, that's now coming from the blue interval, so I'm using the blue expression. And the limit as x approaches 2 from the right of the function called f of x is going to be 2 minus x. So that's 2 minus, well, 2. And 2 minus 2 is 0. That's not 4, so we're not continuous at 2, that's for sure. Now, if these guys are different, it's automatically a jump. I don't really have to do any more math. I don't have to give a darn what f of 2 is. But I know what f of 2 is because 2, again, belongs to the green interval. So f of 2 would come from the green expression, and we may as well say that we know that f of 2 is, again, 4. But it doesn't matter that the function is equal to this limit. It's the two limits that matter, because as soon as the two limits are different, you can state that f of x has a jump discontinuity. at x equals 2. And that's that. We've now done everything we need to do. We've said that we're continuous at 0, and we've proven it with limits. We've said that we have a jump discontinuity at 2, and we've proven that with limits. And we've stated the intervals on which we are continuous. And because we were continuous at 0, we could combine those two intervals. We could go from negative infinity all the way to 2, and then we could go from 2 to infinity. So there's everything you would have to do with that problem. And whoopsies, my face is in the way. Move my face. Yoink. So there's everything. Let's keep going. 8. I mean E. Yeah, okay. That makes sense. 8 is a number that starts with E. I said you don't have to worry about this function. This again is the greatest integer function when you have these double bars. There's going to come a day when I guess I'll say that you have to actually understand this, but today's not that day. But just one more time. The greatest integer function says that at 0 you're getting 0, then you're getting 0 everywhere else until you get to 1. When you get to 1, you hop up to 1. But anything bigger than 1, you just get 1, 1, 1, 1, 1. Until you get to 2, then you hop up to 2. Because this function takes things and just rounds them down. So when you get to 2, it's 2, and anything slightly bigger than 2 is 2, but once you get to 3, it hops up to 3. That's the behavior of that function. So you might ask, okay, so what happens if I divide by 4? Well, dividing by 4 is the same as multiplying by 1/4. So you might remember that the effects of multiplying on the inside is that we get horizontally expanded or contracted. And for numbers less than 1, we actually get horizontally expanded. So if this used to be 1, this gets multiplied by 4. This is now 4. And this would be 8. And this would be 12. And this would be 16. So I don't even know what we're doing anymore. Oh, they wanted us to just talk about the continuity. This is a weird one. We would have jump discontinuities at every single multiple of 4. So you guys that were paying attention a while ago when we were doing trig with tangents and whatnot might remember that we could model all of these numbers by saying there are jump discontinuities at all x's such that, all right, here it comes, x equals, what would it be, 4k, where k is an element of the set of integers. All right, again, if k was 0, then I'll get 0, and there's a jump discontinuity there, right? And if k was 1, I'd get 4. There's a jump discontinuity there. If k was 2, I'd get 8. There's a jump discontinuity there. If k was 3. So essentially that's what you're doing. When you say k is an element of the set of integers, you're saying that k can equal 1 and 2 and 3, etc. But it can also be -1 and -2 and -3. And you're also saying it can be 0. So this expression would be the only way to really say where all these jump discontinuities occur. And this expression is another reason why you don't have to do this problem. I don't want you to know about this function. And I don't want you to worry about having to do this whole thing, although you learned it in everyone's favorite math class, pre-calc. But don't worry about it. Everything I said is garbage. You can fast forward the video. Oh, too late. You already watched it. Moving on. Okay. This one says state the intervals where f is continuous. So, okay, sure, fine. What is this? Factor it. If you try to factor, then in the denominator you certainly need a 3x, and you certainly need an x. Then what are the other numbers? Well, don't forget when we do this, we're going to multiply the outers, and we already have a factor of 3. Then we're going to multiply by the inners, and we don't yet have a factor of 3. And who are we testing? You always multiply a by c, right? So -24. That'll give me a 1 and a 24, a 2 and a 12, a 3 and an 8. 4 and 6. That's all my possibilities. What am I after? -5. 3 and 8 is going to do it, as long as you let the 8 be negative and the 3 be positive. So there's your pair. Again, if I already have a 3 and I want a 3, then I'm gonna just plop a +1 here. And now my outer product will be the positive 3x. Then my inner product is trying to be the 8, the negative 8. And so times 1, I need a negative 8. And that'll give me a negative 8. So again, that should be how you're thinking this through in your head. The way I have this set up now, the 3x times x will of course give me my 3x squared. The negative 8 times 1 will give me my negative 8. And we generate the middle term by doing the outer product and getting 3x. The inner product and getting negative 8x. And those guys add up to negative 5x, which is exactly what we wanted in the middle. So there's your factored form. But honestly, I don't super care. These cancel. I don't super care because it doesn't say classify the continuities or the discontinuities or nothing. But, you know, it might. So this cancels. It's still a discontinuity, though. There's another discontinuity over here that would be what? If this equaled 0, you'd add 8 divided by 3. So it's positive 8/3 and negative 1. And if those are where my discontinuities are, then I must be continuous on the interval that goes from negative infinity up to the negative 1. And then from the negative 1 up to the positive 1. And then the positive 1 up to infinity. So if you have 2 discontinuities, you'd have 3 intervals on which you are continuous. That's all this question asks for. I hope you would be able to say that, of course, the discontinuity at 8/3 comes from a vertical asymptote, so this one happens to be infinite. This one comes from a factor that canceled, so this one happens to be a point discontinuity, and I hope that you could justify it with limits. All right, part B is a weirder one, and as I said in class a handful of times, probably the best way to know this one is to just remember that we already did absolute value of x over x as a function. And we already did the absolute value of 9 minus x over 9 minus x as a function. And somewhere else we also saw, I don't know, something else. But suffice it to say, we started with this quote-unquote simple version. Let me get my face out of the way again. I'm going to shrink my face too. Sick of looking at it. Yoink. Okay, there I am. Okay, so what happens here? We said that this ends up being just a function that it equals negative 1 on the left, and it has a hole at 0, because if you tried to plug in 0, you get 0 over 0. Then on the right, it's positive 1. So it's these two horizontal lines. Now, 9 minus x behaves the same way, except it doesn't have its jump discontinuity at 0. It has it at 9, because the 0 of the denominator is 9. So if you go way over to 9, you'll get your jump discontinuity there. And you're not positive 1 on the right, because imagine plugging in 10. If you plug in 10, then you would get the absolute value of negative 1 over the absolute value of, or over just regular negative 1. That would be positive 1 over negative 1. It's the right-hand side that is actually, that's actually negative, because we're getting negative 1 on this side. And if you plugged in 8, then 8 would give 1 over 1, which is positive 1. So on the left-hand side, we're positive. So there's your two little branches. And guess what? Part B is really no different. For part B, if you were trying to sketch this out, then you would know that the 0 of the denominator is negative 7 divided by 2. That's negative 3.5. 1, 2, 3, 4. Negative 3.5 right here. So I know I'll get a jump discontinuity here and here, giving me 1 and negative 1. Which way, though? Well, positive values, or I don't know, just test 0. Plugging in 0 gives positive and positive. Yeah, so we're positive. So we're going that way. So the other side is the negative side. None of this matters all that much because you weren't really asked to do all that much. You were just asked to say where we're continuous. And so looking at the picture now, you can see that we're continuous from negative infinity up to the 0 of the denominator, negative 7/2. And then we're continuous again from negative 7/2 to infinity. Expect the follow-up question, of course, where I say, what type of discontinuity do you have? And you'd say jump. And I'd say prove it using limits, and you'd say the left-hand limit is -1, but the right-hand limit is +1, so it's a jump. Ooh, please tell me this is starting to make sense. All right, getting into the second one now. How do I actually evaluate this limit? To evaluate this limit, welp. A lot of you guys were feeling good about how, like, ooh, I have my calculator. I can just graph it and look at it. Well, no, you can't. Of course you can't. I'm expecting you to show work. So what work do we show for this? I mean, ideally, the work you would show is just plugging in the 0. But of course, that doesn't work here because you get root 19, take away root 19, all over 0. That's 0 over 0. You can't ever have 0 over 0. That's indeterminate. It doesn't mean that your limit is 0. It doesn't mean that your limit is infinity. It doesn't mean that your limit does not exist. Your limit could literally still be anything. So you have to go back and do the math. And the math for a problem like this was to multiply by the conjugate. So you get root x plus 19 plus 19, or root 19. And you multiply that on the top and the bottom. And what happens when you do? You're going to FOIL. So this radical times this radical, the radical cancels and you just get x plus 19. Then the outers and the inners cancel each other out because you get positive this and negative that, and they cancel. Then negative root 19 times root 19 is a minus 19. This would be all over. The denominator you don't mess with. It's just going to be an x times the whole conjugate. Okay, and please, please, please don't forget, this is still a limit. You must actually write limit in front of this. You can't save time by leaving it out. You're going to lose points if you leave it out, so put it there. All right, what's happening upstairs? These parentheses we said aren't really doing anything. Go ahead and get rid of them. 19 take away 19 makes 0, so you got a factor of x. And that factor of x does in fact cancel with that factor of x, giving you now the limit as x approaches 0 of, well, nothing's left up here, so there must just be a 1 left up there. So it's 1 over the root x plus 19 plus root 19. And at this point, you can plug in 0, because plugging in 0 now doesn't give you 0 over 0 anymore. So finding the limit by just plugging in is now a valid strategy. So I'm going to plug in, which means I now don't write limit anymore. I get 1 over 0 plus 19 plus 19. That's a radical. That's a radical. That's 1 over root 19 plus root 19. And when you're adding radicals that have the same radicand, like if you had root n plus root n, that's just 2 root n. You don't change the radicand. By the way, if this was 3 of these and 5 of those, that would just be 8 root n's. That's how that works. So this is 1 over 2 root 19. And I said you don't have to worry about cleaning up radicals from your denominator, so go ahead and give that as your final answer, and that's A-OK. All right, next. All right, this guy again, I forever live in hope that maybe I can just plug in, but -3 plus 3, that kind of shatters my hope because it looks like I'm getting 0. But you never know, maybe the denominator won't be 0. -3 squared plus 2 times -3, take away 3. That's, of course, positive 9, take away 6, take away 3. Ah, damn it. That's 0. So because I'm getting 0 over 0 again, I have to just start all over, and I have to clean this up. And I don't think any of you would have done that anyway. You all probably would have jumped straight to factoring, and I think you'll notice that somebody cancels. So this is now going to be the limit as x approaches -3. Of what? An x plus 3 over, you guessed it, an x plus 3 and an x minus 1. So that guy cancels that guy. So you now have a new limit expression where you're taking the limit as x approaches -3 of 1 over x minus 1. And this guy doesn't equal 0 over 0 when you plug in anymore. So go ahead and do the plugging in. This will be 1 over negative 3 take away 1, which is 1 over negative 4, which is negative 1/4. So that's 2 limits down. This one I said you could go ahead and not worry about. This is more complicated than I would throw your way. So forget that one. Yeah, forget that one. Because I don't care. This one. Hey, this looks familiar. Doesn't this look a little bit like that function we were talking about before? Which at positive 2 should have a jump discontinuity that goes from negative 1 to 1. And to the, let's do the left because it's easy to plug in 0. If I go to the left, then I'm getting absolute value of negative 2 over negative 2, which is positive 2 over negative 2, which is negative 1. So for sure the left side is at negative 1 and the right side is at positive 1. And if you can kind of quickly walk through that, then you can evaluate this limit graphically instead of algebraically. You can just say, hey, I looked at my graph and the limit as I approached 2 from the left hand side was giving me negative 1. And that's the answer. The other thing you could do, like what the answer key shows, is the answer key shows just a numerical approach where they basically just plugged in 1.999 to see what happens. And plugging in negative or positive 1.999 gives the absolute value of negative 0.0001 all over negative 0.001, which again would be positive that number divided by negative that same number, which of course is a 1, that is negative. So a numerical approach here is pretty valid. A graphical approach is pretty valid. If you try to do it algebraically, I don't know if it would work so well. I'm not even going to begin to explain how you would do it algebraically because it would take a while, and it ain't worth it. Just do that one graphically if you have the chance. I don't know why I erased everything. That was stupid. There, it's back. All right, let's do the next one. It looks to me like another rational. Certainly the first thing I would do is factor and hope that things cancel. And of course they do. Because when I factor I get x. I want 5, so 5 and 10. I want a negative 5, so negative 10 and a positive 5. And then there's an x minus 10 in the denominator. Hey, what did I do wrong? Nothing really. I just haven't done it yet. But you have to bring the limit down. You have to bring the limit down. I will mark you down if you don't. Okay, cancel those. At this point, you don't really have to rewrite everything. You can just go ahead now and say, so this limit will be a10 plugged in for x plus 5, which is 15. Apparently that limit is 15. That's it. Now 9 is a good one. For 9, can I just plug in? I'm sure the answer is no, but let's try. If I plug in 0, I get 1 minus 1, which is 0 over 0, and nope, I can't. So what do? You have to combine fractions. So in the numerator, we're doing the limit as x approaches 0 of, well, this is 1 over x plus 1. So my common denominator, if this is 1 over 1, would be x plus 1. So you're multiplying this by x plus 1 over x plus 1. And then the whole thing just becomes x plus 1 over x plus 1. And this is a subtraction problem. And in the denominator, I just have x. Although it might be nice to think about that x as an x over 1. But here's where we're at. So what happens next? You get the limit as x approaches 0 of, you're getting 1 minus, remember it's the whole thing, x plus 1. So the minus distributes onto the x and onto the 1. So what you really have is 1 minus x minus 1. And then of course the 1 minus 1 will cancel each other out. So your numerator will just be negative x. Your denominator will be the x plus 1 that they share. And then if you're smart, you're going to rewrite this where instead of dividing by x over 1, you're multiplying by 1 over x. And then you'll watch with glee as this x cancels this x. But you'll also notice that this negative sign did not cancel out. So your numerator still has a factor of -1 in it. That means we are now calculating the limit as x approaches 0 of -1 over x plus 1. Which means when you go to plug in 0, you're getting -1 over 0 plus 1, which is -1 over 1, which is -1. And that's that limit. Okay, great. Finally, a change of pace as we get to 11, 12, da 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 da. This is one of those problems where I'm giving you a graph and you just have to read off of it. So let me make that graph scotch bigger. Boink. That's a little bit bigger. I'll make it even bigger. Although it has a stupid orange circle on it now, but I can live with that. All right, I hope this part's easy. This will be on the test for sure, but I hope you'll find it simple. It's asking for the limit as x approaches 3, and 3 is here, of course. So what happens as I approach 3 from the left? Well, I get 2, of course. It doesn't matter that it's a whole, remember? Limits are defined by the y values that they approach. They are not the y values that you actually get. They're the y values you come close to. And I'm coming close to 2. And if I come in from the right-hand side, I'm still coming close to 2. So since left-hand limit equals right-hand limit equals 2, this limit is 2. And as I head towards 1, 1 is right here. And this is the same deal. This is another removable discontinuity. So the limit as I approach is given by the whole. And this dot doesn't mean anything, for the limit at least. As I approach 1 from the left, I'm getting 4. And as I approach 1 from the right, I'm getting 4. So my bidirectional limit is 4. Now, if you feel bad for this poor dot over here, that's lavender, that's f of 1. If you're actually evaluating the function at 1, that's when you use the dot to get your 2. Okay? And same with 3. This hole over here, if I was actually evaluating the function at 3, then that would be undefined because there's a hole there. And so the hole would make us undefined, even though the limit exists. Okay, what's happening at -2? -2 is over here. I see a jump discontinuity. So what's f of -2? Is it 2 or is it -2? Well, of course, the function value is given by the filled in circle, not the hole. So this is -2. So what's the limit at -2? Oh, that's not -2, that's 2. So here, 16 and 18, and they didn't ask, so I'll just pretend they did. But imagine if there was a secret number 19 that asked for the limit as x just approached -2 bidirectionally. Then these would be different answers. But the limit from the left, that's 18. That would have me following this parabola looking thing, and I'd be getting a limit of -2. But the limit from the right is going to have me following this line down to here, and I get my limit defined by the hole, which is at 2. And then, of course, the bidirectional limit, if the left side is -2 and the right side is +2, then this limit would not exist, does not exist. And I haven't done 15 yet. 15 is asking for the limit at 2. That's here, where there doesn't seem to be anything special going on. But there's still a dot here. We're just continuous there, which means the limit there is the same as the value of the function. It's 3, because left-hand limit, 3. Right-hand limit, 3. Value of the function, 3. Bidirectional limit, 3. This is obviously 3. All right, that's everything. So I hope you feel good about that. There is something kind of distinctly missing here, though. So let's pretend for a hot moment that this graph actually ended at 4. And let's pretend that it ended at a hole. And let's pretend that right there was a big old vertical asymptote. And that just for a shining moment in time, I don't know, maybe we had a log function, goes up, 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 and levels off like that. All right, if you had this vertical asymptote, then I might ask you, what's the limit as x approaches 4 from the left? What's the limit as x approaches 4 from the right? I might ask you what's the limit as x approaches 4, just in general, bidirectionally. And of course I could also ask you what is f of 4. And all those answers would be, well, let's see. As I approach from the left, I just follow this branch, and I seem to end at a hole, which is giving 1. As I approach from the right, I'm going to follow this asymptote all the way down, and my limit would be negative infinity. Now, because those limits are different, would say the bidirectional limit does not exist. And if I asked you for the function, well, we end at a hole, so there's nothing. And there's an asymptote, so there's nothing. And if there's nothing, then we are undefined. Ugh, that's it. This was 35 minutes, this video? Yikes. Alright, I said I was going to go back. Oh, I'm not even done? Okay. Why don't I stop here and get this posted so people can look at this, and then we'll make a part 3. Goodbye.